Hi, guys. How you guys doing this morning? Okay, good. So what's happening on campus at Thanksgiving? Are you guys, for those of you who are on campus, are you going home and then staying home for the rest of the semester, or what was happening?
Me, I'm going home Sunday.
This Sunday? Oh wait, so you're wondering if the homework for 1.1 part 2 has been changed? Lecture examples were attached instead. Oh, that means I made a mistake when I attached it. I will fix that. So that means that you guys don't have the homework for chapter 1.1 part 2? Let me do that right now. Let me just check really quick. Give me a second. Let me check that really quick. Okay. So that would be, why is it doing this? My computer's doing weird things. Hang on. Chapter 1.1 part 2. Give me just a second to see what it looks like. Oh yeah, you're right. I'm sorry. You're right. Lecture examples, that's wrong. Let me fix this. Let me edit this. I apologize. Let me go fix the, I'm gonna fix the homework for that right now. Insert, upload. Give me a second. I'm gonna upload the correct homework. So homework chapter 1.1 part 2. Homework there, that should work. And then let's see if I can't get rid of this one. There. All right, try that. Let me see, hang on, let me, is there a way I can save it? Let's see, I can't see the window here. Save. All right, why don't you go ahead and take a look. Take a look at the homework right now for chapter 1.1 part 2. It is, it should be correct. Thank you for letting me know. I actually had not realized that I had uploaded the wrong file. Okay. So go ahead and check out that homework. Thank you for letting me know about that. Okay. So good, you're going home and coming back after. You're going home and staying until spring semester. Coming back after a week. Is this been changed? Okay, good, thank you. Good. Yeah, good. Well, for those of you guys who are going home, but who are going to be still coming to lectures, you are in luck because everything's remote. So you can log in and get your lectures. And if you can't do it live, obviously, you know, I post the lecture videos, you know, within a couple hours after our class. So you should be able to get a copy of the lectures after that. So that's good. All right. Hey, you guys. So we are going to start chapter 2.1 today. Which I'll talk about in a minute, but we have a quiz tomorrow on chapter 4.1 and 4.2. 4.2 includes part 1 and part 2. Does anybody have questions on homework for chapter 4.1 or 4.2 that you'd like to ask? I can work through some problems. We have time. Chapter 2.1 isn't a very long chapter. 4.2, number 69, and 57. All right, let's do this. So, 4.2. We'll do them in order. So let's do 57 first, and then we'll go up to 69. All right. So this is homework, chapter 4.2, and we're going to do question 57. All right. So let's do this one first. Okay. So this one. So we've got 1 over x squared plus a squared dx, right? Where a is not equal to 0. So remember, we actually talked about this in class when we did our inverse trig functions. We're going to solve this two ways. We're going to solve it like we recognize this is our inverse trig. This is our inverse tangent function, right? So basically, this is our general solution for our inverse tangent function, which is 1 over a. That's an a. 1 over a inverse tangent of x over a plus c. But let's go ahead and do it long way. So this is our answer, you know, basically recognizing the general form for, but let's do it long way by substitution. So you can actually see where this form comes from. Okay, so bear with me here as I work through. It's going to seem kind of convoluted. So basically the process that we're going to do this is we're going to divide numerator and denominator by a squared. Okay, so if I divide the numerator by a squared, what I'm going to get is 1 over a squared in my numerator, and then I'm going to get each term gets divided by it, right? So this is going to become x squared all over a squared plus a squared all over a squared, and there's a dx right here. Okay, so now what this is 1 over a squared right? So all I did, this is x squared over a squared, so I made it one big lump, x over a quantity squared. A squared over a squared is just 1. This is 1 over a squared. So 1 over a squared is a constant term. I can bring it through my integral. Okay, so this is going to look like 1 over a squared, the integral of 1 over x over a quantity squared plus 1 dx. And now I can start thinking about substitution. So I'm going to substitute this. This is my more complex thing, right? So I'm going to substitute u equals x over a. Notice how I didn't do u equals x over a squared. I'm looking at the innermost function, right? So then what happens is u equals x over a, which this is like 1 over a times x. So then my du is just going to equal to 1 over a dx, which when I multiply this through, this is going to become a times du equals dx, right? I just cross multiplied. So I'm going to substitute that for here. I'm going to substitute that for there. So this is going to look like 1 over a squared, 1 over u squared plus 1 du all over, du times a. This a is actually just a constant, so I'm going to bring that through my integral. So that's going to look like a all over a squared, 1 over u squared plus 1 du. You know, I did this here so you can see, right? The a and the a squared, I'm going to be able to cancel out one of those. This is going to look like 1 over u squared plus 1 du, right? So now this is our inverse tangent form, right? So it looks kind of like what we're familiar with. So now I've got this 1 over a inverse tangent of u, and then I've got my plus c. I have to substitute back because we started off with things in terms of x. Now we have to make it, we have to get rid of the u. So this is going to become 1 over a inverse tangent. Remember, we substituted. So this becomes x over a and then plus c. So this is like where our general form comes from, right? 1 over a inverse tangent x over a plus c, showing you how we got there through substitution. Right? Whew, it's a lot. But it's important to kind of know like where that general form comes from. So, and then number 69. Okay. All right. Okay. I'll give you guys a second to finish writing that, and then we'll move on to question 69. Remember, I'm going to post the videos later too, so that in case I'm writing this too fast and you need time, take a look at the videos later. You can pause it, or you can take a screenshot. I had students in my 8 o'clock class take screenshots of things so that they can do that. All right, so would we say number 69? So this is same chapter 4.2. So let me just write down L equals 3, V of t equals t squared plus 1. I of 0 equals 0. So v of t equals L times di dt. So plugging in for L, we're going to get 3 di dt equals t all over t squared plus 1. Okay, so now, right, I'm going to do separation of variables. Right, where I bring the dt up over here. So I have 3 di equals t all over t squared plus 1 dt. Right, now I need to integrate to get things in terms of I and t. Right, so I'm going to integrate both sides. Okay, so now we're left with 3 times di is just 3 times I, and that's going to equal to, let's see, how can I do this? I'm going to do use substitution, use sub. So u is going to equal to t squared plus 1. My du is equal to 2 times t dt. Well, I have a t dt, so I'm going to divide both sides by 2. So I'm going to get du over 2 equals t times dt. So I'm going to substitute t dt with du over 2. I'm going to substitute t squared plus 1 with u. Okay, so then this becomes, I'm going to factor out this 1/2. So this becomes 1 over u times du. Much more simple, right? Whenever I see 1 over u, this is u to the minus 1. This means our natural log. So 3i equals 1/2 natural log, the absolute value of u. Don't forget your plus c. Now we need to substitute back for u, right? So I'm going to substitute back into there. So I'm going to get 3i equals 1/2 ln absolute value of t squared plus 1. In theory, I probably can drop the absolute value because with the t squared, I'm always going to have a positive term there, but I'll just leave it for now. And now I'm going to use our initial condition to solve for c. Okay, so remember our initial condition we were given here, I at 0 equals 0. So that means I can say, oh, I want to divide by 3 here. I'm going to divide both sides by 3. So I'm going to get I equals, so this is 1/2 times 1/3, so that's 1/6 ln t squared plus 1 plus c. Okay, so now this is I of 0 equals 1/6 ln of 0 squared plus 1 plus c. So then this becomes ln of 1 times 6, so 0 times 6, so c equals 0. Okay, so I'm going to put that back here into this equation here, okay, to get my final equation. So I'm going to call I as a function of t, which is 1/6 natural log t squared plus 1, and then plus 0. I don't need to add the plus 0. Okay. It's probably a good practice just to leave the absolute value. I've seen people on final exams, take off points if you don't have the absolute value for sure. You need to have it here. But I mean, I've seen you can maybe rationalize your way through, but just leave it. It's not going to do any harm. Okay, so that's 69. We want to do number 44 on homework 41, 4.1. Do you know, I got to tell you, 44, I think I just posted 44 up on our website, so on our Canvas page. So question 44 of chapter 4.1 is on our modules page. I think it may be last week for week of November, has November 11th in our holiday week. Wherever 4.1 was assigned, I did a detailed solution for it. I scanned it in yesterday. I put it up there. So go ahead and check that there. And then you guys, if you have any questions about it, later you can ask me, but that's the example that we would have had there. So question 39. Yeah. So question 39 was like, it took me about 2 pages to do. So let me do this. I am gonna scan in so chapter 4.1 question 39. It was like, from when I did it, it was about like a 2-page answer. I mean, I know I write big, but I'm gonna scan that in and then post that because we'd be here all morning for me writing that up. 4.2, number 22. All right. So 4.2, question 22. Okay, let's take a look. So this one says h of x equals 4x squared plus 4x plus 9. Big H of -1 equals 2. So little h is our derivative. Big H is our antiderivative. This is an initial condition, right, that we're going to use to help us solve C. So we're going to go the integral of h of x plus c, right, is going to equal to integral of 4x squared plus 4x plus 9, right? So this is using linearity. So now what we're going to do is I'm going to go integral of 4x squared dx plus integral of 4x dx plus integral of 9 dx. Okay, when I go to integrate this, right, the 4 comes through, right, my integral. Now I've got my power rule on all of these. So this says I'm going to increase my exponent by 1 and then divide by that new exponent. I've got the 4 that floats through. My exponent increases by 1. This is actually times x to the 0, so this is going to become x, and there's going to be a plus c in there. So now this is equal to big H of x. So now I can say big H of -1 equals 2. So I'm going to go 4/3 minus 1 cubed plus 4 divided by 2, that's 2 minus 1 squared plus 9 times -1. And when I add it up, sorry, and then there's a plus c. And when I add it all up, right, what I'm going to get is 2 equals, let's see, minus 4/3 minus plus 2 minus 9 plus c. And then I got, there's some algebra involved. I get c is equal to what I get, 31 1/3. So I'm going to do that right here. I'm going to plug in my c value. So I'm going to get my big H of x. 4/3 x cubed plus 2x squared plus 9x plus 31/3. 59. All right. Yeah, this is another one where we're doing a generic form of our sign. Question 59. Our inverse sign. So this is question 59. Right, so this one we're asked to integrate 1 over a squared minus x squared square rooted dx. A is greater than 0. All right, so now I have to do a bunch of things. All right, let's think about it. So what I'm going to do is I'm going to factor out an a squared here, right? So it's going to look like, I'm going to do this. I'm going to go 1 over, I'm going to get a squared times, it's going to be 1 minus x over a quantity squared. Okay, because like if I were to multiply, this would be like x squared over a squared. If I were to multiply, then that would just become x squared. And this is, so I'm back where I started from, right? And this is dx. Okay, now I can take this out, right? So this becomes 1 over a radical 1 minus x over a squared dx, which 1 over a I can take out of my integral because it's just a constant term. Sorry, that's an a. Okay, now I can do use substitution, right? Where u equals x over a, du equals 1 over a dx. So then a times du equals dx. Okay, and there's a dx right there. Okay, so now what we're getting is 1 over a, 1 minus u squared there, and this is a times du, right? The a comes out, a over a. Oops, sorry, du. There's a du there, right? So this is our inverse sine, right? A over, I'm showing you this a over a so you can see where all these letters are going. So then this becomes inverse sine of u plus c, and then we need to substitute back. So that's going to become inverse sine. So our u was x over a. We actually talked about this when I gave you the formulas for our inverse trig functions. I told you the generic form, which was a squared minus x squared, instead of it being a 1, you know, when a was equal to a 1. But this is why, this is where it all comes from. Okay, so instead of just recognizing, oh, that's our generic form, it's just going to be this. This is why. And this is the process for how we're actually doing it. 4.2, number 5. Okay, give you guys a chance to finish writing that. Then we'll do question number 5. This is chapter 4.2. Okay, so this says 1 over y plus 1 over 1 plus y squared dy. We want to integrate that. So you use linearity, 1 over y dy plus 1 over 1 plus y squared dy. Right, so this is y to the minus 1 dy. Right, so that means I need to use the natural log. This is one of our inverse trig functions, right? It's our tangent function, okay? So that means I'm going to get natural log of the absolute value, don't forget your absolute value, plus the inverse tangent of y, and then don't forget your plus c. Okay, and 15. Okay, oh yes, it's a good one, 15. 5 over x ln of x dx. This one pops up a lot in calculus 2, and then it gets used a lot when we want to test you on things, because it's, you know, kind of tricky. Which one do I think about? How do I do this, right? So this is also going to be a use substitution problem. But the question is, like, what am I using as you know, my use substitution and my variables? So what I'm going to do is, before I jump into the use substitution, I'm going to break this apart. So I'm going to take the 5 out, and I'm going to say this is 1 over ln of x times 1 over x times dx. Okay, so that should help you kind of visualize, right? So I took the 5 outside my integral because it just passes through. This is 1 over x ln of x, but that's like saying 1 over ln of x times 1 over x times dx. Okay, so now when I want to think about what I do for use substitution, I need to think about, is there a derivative in there, right? 1 over x is the derivative of ln of x. Don't be fooled by this being 1 over. Okay, don't go into, you know, crazy gyrations on like how you're going to substitute and where you're going to put things. This becomes our u. So u equals ln of x. du is just 1 over x dx, which we have. So this becomes our du. So then this whole function now reduces down to 5 times 1 over u times du. Okay, which this is u to the minus 1 du. So I'm going to go 5 natural log of u plus c. Okay, now I'm going to substitute back. Right? So this is going to become 5 times the natural log of the absolute value of natural log of x plus c. It's okay. I can take natural log a bunch of times. It's all right. Make sure if you're taking the natural log as a result of doing the function, that you use the absolute value signs. Okay, I'll just do these last two here, 17 and 19. Wait, 17. Was that on? I don't think we have. I don't see 17 as, we don't have to do 17 on, oh, I see that's 4.1. Sorry, I'm looking at the wrong one. Looking at the wrong chapter. 4.1. Okay. Okay, so 17. So this is chapter 4.1, question 17. So give an explicit solution to dA dt equals t a squared, where a of 0 equals 6. So our two solutions are a of t equals 0, which is a trivial solution. And this is, by the way, from our book. I think the book did this problem out like exactly. So you're just kind of copying it down. You're taking a look at what they have in the book. So that's one of them. And then the other one is a of t equals 2 all over c minus t squared. Okay, these things come right from our book. Okay, so we're going to solve for c in this equation right here. Okay, so we're going to discard this one because it's trivial. Right, it's just equal to 0. All right, so I'm going to say a of 0 equals 6. Like it doesn't work here with that equals 0. So I'm going to go equals 2. I'm going to plug this into here, c minus 0 squared, right? So I'm plugging in 0 for t. So then I get, do some algebra, and I'm going to get c equals 1/3. Right, so now I can plug that in. So then the solution is going to be 2 all over 1/3 minus t squared, which you can rework if you want to be 6 all over 1 minus 3t squared. Both of these are fine. 19 is just 19 is just words, general versus particular. I'll show you what I have for 19. You guys have that there? So this is what I have for 19 here. You guys can take a look at it. The general has some parameter like ABC, which allows your solution to be applied to any initial condition. The particular solution has a specific value for these parameters, and it links it to the specific problem at hand. So that's it. You're just talking about words. Okay. Okay, guys, let's go ahead and move on to chapter 2. So today we're doing chapter 2.1. Let's see, where are we here? There. So chapter 2.1. 2.1 is called Sums and Differences. Okay, so in chapter 4.1, 4.2, which is also like chapter 1 of the integral calculus book, we talked about integration, right? We started talking about antiderivatives, we talked about integration, we talked about power rule, we talked integration by substitution, and then integration by parts. So we're learning some tools for integration. We're going to take a step back now and think about what's going on behind the scenes when we integrate. When we integrate things, like if I want to integrate, now all those integration and antiderivatives that we did before were on indefinite integrals. They didn't have bounds, right? So I just had an integral without any kind of a to b. But if I want to take an integral from a to b, right, it's like a whole, it's not just a process of taking the integral, but it actually means something geometrically. So we're taking a step back in chapter 2.1 and we're starting to think about that geometry. So we need to have some tools in our toolkit for how we handle some things. Plus, in terms of sums and differences, like when we talk about a sum, I'm talking about like a summation, right? And so we need to understand summations because we're going to be using them a lot in calculus too, to describe complex functions as summations of polynomials, okay? So we're going to kind of build up some ideas and definitions around summations and things that we can do to simplify them and make them a little bit easier, okay? So this is what chapter 2 is about. So we're taking a step back from integration and learning some more fundamental stuff about stuff. So there are a lot of definitions. There's some examples you can see. Have the lecture examples for 2.1 up already, but a lot of the examples that we're going to do apply to these things. We just have a lot of definitions. It's kind of chapter isn't as, you know, kind of hands-on. But let's go ahead and start working. So our first definition. what is the summation? Right, so I've got, let's talk about, I've got m and n are integers, right, where m is less than or equal to n. And then we have some interval of integers that starts at m and it goes to n. Okay. We have some function f. Our function f has a domain which includes this interval. And I want to have all those interval values within the domain of my function. So my summation is going to look like, right, I'm going to go k equals m to n, some function, whatever f of sub k is. It could just be k, it could be some complex stream of polynomials, it could be, sines, exponentials, whatever. It's a function, right? And so I always think about summations. My background's computer engineering, so I think about summations in terms of like a for loop, right? The k is my dummy variable, m and n are my indexes, right? My indices into this summation. So m tells me where to start. I'm going to start at 0. I'm going to go up to 5, or I'm going to start at 1. I'm going to go up to infinity, say, for example. So this tells me like how many times through the loop I need to do. Okay, so I start off with my first value, and then I increment it by 1, and I sum. I add whatever that function is. I add the next term, and I'm adding because this says I'm going to sum, and then I keep going. I'm going to keep adding n minus 1 up until our very last term. So we're adding up all of these different terms. I got my lecture examples here. I'm going to do a couple examples here so you can start to see what these things look like. So let's try example number 1, which is summation k equals 1 to 3 and minus 1 to 3 of k squared. Okay, so k squared is our function. For every value, I'm going to square it. I'm going to add it to the next one in my loop. So this means when k equals minus 1, I'm going to go minus 1 squared plus. The plus comes from my summation. K equals 0. So this is going to be 0 squared plus k equals 1. 1 squared plus k equals 2. 2 squared plus k equals 3. 3 squared. Summations can go on forever, right? I mean, we stopped at 3. I could have stopped at 1,000. Or I could have stopped at infinity, right? Which means I'm here forever doing this stuff. Okay, so I'm going to add these up. So this is 1 plus 0 plus 1 plus 4 plus 9, right? I'm squaring it, and I'm going to add all those terms together, which gives me 15 when I add them all up. Okay, summation's just a loop. Add, take this function, plug in this value into that function, get a number, add the next one to it, increase the value that you're going to do by 1. It's an integer, and then keep adding it until you reach the end of your loop. We use summations to write polynomials. I know we're used to thinking of polynomials in terms of the highest degree term and then all the way down to the lowest to our constant term, but we're going to start writing them in the opposite direction, where I have my constant term. And then I'm going to start building up. I'm going to write x to the 1 just so you can see that this index is the same as that index. A2 x squared plus a3 x cubed plus so on and so forth, all the way up to wherever we tell it to end, if we tell it to end at all, which I can write as a summation. I can say this is k starts at 0, and it goes up to n. And I've got my coefficient a sub k x raised to the kth power. Okay, so this is our polynomial, right? All written out in terms of all the individual terms, and this is our polynomial written in summation form. This is important. We're going to be using this a lot next semester to represent really complex functions, and we're going to need to be able to know how to manipulate these summation of polynomials, like to do, integration, addition, multiplication, division. It seems like, oh, how's that going to work? You're going to learn it, okay? But this is how we're starting to lay the foundation right now, okay? So I said there were a lot of definitions. Here's your next one. Definition. How do we split a summation? what does that mean? So I've got m, n, and p. These are integers, right? Such that m is less than n, which is less than p. So I still go from m to p, but I'm going to have a stopover point somewhere in between, okay? And I've got f as my function, and the domain includes m to p. Okay, it's important for that to be on there. So now I've got my summation, k equals m to p, f sub k equals, right? Watch what I'm going to do. K equals m to n, f sub k plus. I'm going to start off at the next integer up from here, k equals n plus 1, and I'm going to end at the end. So m to p, those form the beginning and the end, ultimately of where I'm going. I have a stop off point here. Okay, I don't want to start at n here because I'll double count it. Okay. Okay, if n equals p, our last sum is going to be equal to 0, so we don't double count. Okay, so we're going to split this summation here. Example number 2. And I didn't tell you where to split it. We're just going to split. I'm going to just go ahead and show you how we can split it up. Okay, so what I'm going to do for here is I'm going to split this into j equals -1 to 0, j squared, plus j equals the next one up, 1 to 3 of j squared, right? So I'm doing integers. Notice these indices are all being, they're all integers, and I'm incrementing by 1 each time. So this looks like, let's do this loop here. So I'm going to go -1 squared plus 0 squared plus, that's this plus right here. So then I'm going to go 1 squared plus 2 squared plus 3 squared. So this is 1 plus 0 plus 1 plus 4 plus 9. You can see it's the same thing that we had before, right? So that's still equal to 15. Why do we want to split summations up? Why not just do it? Well, we split things up because it will allow us sometimes to combine summations with others. Okay, so it allows us basically to say, oops, sorry, I'm going to go from here to here, but I'm going to do this part first, and then I'm going to do that part. Well, maybe this part is the same, has the same index, k equals 0 to 5, as some other summation that's k equals 0 to 5. Then I can combine those two into one summation, save myself some, computational. All right, next definition. We're going to shift our indices. Shifting indices is important. It's going to allow us to rewrite our function so that our indices, instead of going from here to here, I'm still going to go from here to here, like A to B, but I'm going to rewrite the function so that the summation looks like I'm going from there to there, but really in the end, I'm still going from here to here. But if I shift the indices, it allows me to combine it with something else. So I've got f is a function whose domain includes m to n. These are p is an integer, m and n are integers. So I'm going to say k equals j plus p, which I can rewrite in terms of j equals k minus p. Okay, so I've got the summation, j equals m to n. F sub j is going to equal to k equals m plus p to the n plus p, f sub k minus p. Okay, that's our definition. We're going to do an example so you can see how we're going to shift the indices of our function. I didn't tell you, how to shift it or how much to shift, but you're going to see how this is a shifting example. Normally you would be told, or you would see, let me just go ahead and work it the way through example 3, and then you'll see, and I'll talk about what you would be given or why you'd want to do it. Okay, so I've got this same thing that we're doing before. So let me just write out, this is -1 squared plus 0 squared plus 1 squared plus 2 squared plus 3 squared. Okay, so minus 1, 0, 1, 2, and 3. Okay, so let's just keep that in mind. So what we're going to do is we're going to replace each j squared with j plus 6, so 6 minus 6 squared. Watch. J plus 6 minus 6 is still j squared, right? So I'm taking j squared, all I'm doing is rewriting it. This is a rewrite. Okay, it's going to allow me to shift this from k equals minus 1 to k equals 6. Okay, you didn't know that ahead of time. I'm telling you, this is an example of how we're shifting it. Okay, so let's go ahead and do it. So now let's think about it. My first one, minus 1 squared, is going to look like, I'm going to plug in minus 1 for j. So minus 1 plus 6 minus 6 squared. Okay, I'm going to combine these two together, right? So then what I'm going to get is 6 minus 7 squared. So minus 1 minus 6 gives you minus 7. This 6, sorry. This 6 here is that 6. This minus 7 comes from adding this and this. Okay. All right. So now if I do that with all the rest of them, right, this is going to look like 6 minus 7 squared. Let's do that with all the, I'm going to plug in, right? So this is where I start off with. Now, if I increase my index by 1, I'm going to increase this by 1. Okay, so now if I go loop through, so instead of having minus 1 squared, which is 6 minus 7 squared, I'm going to add to that. This is going to be 0 squared. So this is going to be 7 minus 7 squared. See how I added 1 to my index? I'm going to add 1 to my piece right there. Plus 8 minus 7 squared. 7 squared. Right, so see how this is 0 squared. This is going to be 1 squared. This is going to be 2 squared. This is going to be 3 squared in here. Okay, which now I can rewrite in summation form. So I'm going to start k equals 6 to 10 of k minus 7 squared. So what I did was I started off with k equals minus 1 to 3, and I've shifted it k equals 6 to 10. Now, in real life, like what's going to happen is you're going to see this right here. It's going to be in some other summation, right? And you're going to want to go, how do I go from minus 1, k equals minus 1 to k equals 6? What do I need to do to make that happen, right? Okay, so this is how we're changing our formula. So instead of k squared, I'm going to go k minus 7 squared. And that shifts this whole thing to be equal to k equals 6 to 10 instead of k equals minus 1 to 3. Why do I want to do this? Because maybe I've got some other summation that has this as my index, k equals 6 to 10. Now I can combine these together. We're going to do an example like that in a little bit. Okay, so another definition. This is linearity of summation. Okay, so now, oops, there you go. Linearity of summation. So A and B are constants. F and G are functions whose domain includes M to N. Okay, so what I'm going to say is K equals M to N of A times F sub K plus or minus B times G sub K, right? F and G are my functions I'm adding. This is the linearity part, plus or minus. Now I can do a summation, K equals M to N of A, F sub K plus or minus summation, K equals M to N, B, G sub K. More often than not, you're going to go from here to here. I'm going to combine them into one. You want to be able to do that when they have the same indices, right? K equals M to N, K equals M to N. I can combine them into one big piece if they're being added or subtracted together. We're going to see how that works. I'm going to show you an example where it's example 4, where we're actually kind of working our way into showing you that this is the same thing. So we're going to do this. So this is going to look like, so I'm going to have 1.7 times, I'm going to start off at 7 squared minus radical 3 sine of 7 plus my next loop through 1.7 times 8 squared minus radical 3 sine of 8 plus 1.7 times 9 squared minus radical 3 sine of 9. Now, you may be wondering, like, why am I worrying about, factoring things and doing linearity on these summations, right? I'm only going from 7 to 9. I can just do it out. It's true. 7 to 9, I can do it out. If I had, like, 1,000 different terms on here, like k equals 7 to 9,000, say, for example, I don't want to do it out. I'm just going to try to figure out a solution for making it work. Okay, so now this is going to look like, right, I've got a 1.77 squared. I'm going to factor out my 1.7 terms. So this becomes 7 squared plus 8 squared plus 9 squared, right? I'm going to factor out my minus radical 3 terms. So that's going to be sine of 7 plus sine of 8 plus sine of 9. Okay, which means I can go 1.7 times the summation, k equals 7 to 9 of k squared, plus minus radical 3 times the summation, k equals 7 to 9 sine of k. I'm showing you that it's the same thing, right? Because how we did it, we factored these things out. And I'm essentially splitting up, distributing my summation, my linearity. Example 5, we're going to do linearity and the shifting of indices to rewrite these summations. And why are we doing shifting of indices is because, look, this one goes from k equals 3 to 50, and this one goes k equals 1 to 50. So if I want to be able to combine them into one summation, I have to shift the indices on here in order to combine these two. All right, so let's go ahead and do it. Okay, so they're different indices. So what we're going to do is we're going to take this bit here and we're going to rewrite into two summations. Okay, you're going to see how in just a sec. All right, so now I'm going to copy this one over. So 2 k equals 3 to 50. I'm going to distribute this k into both these terms. So k squared minus k plus, now what I'm going to do here is I'm going to say, oh, you know what? I'm sorry. There's a typo in here. I forgot. This should be a negative. I'm subtracting. I copied it down wrong for my notes. That's a negative. So I'm going to subtract minus. Right. So watch what I'm going to do. I'm going to take k equals 3 to 50. I'm only going to take that portion, the portion that overlaps here of k plus 1, k plus 2. And I'm going to FOIL that out, k squared plus 3k plus 2. Okay. And then what I have left over is I'm going to go from 1 to 2, right? Because I skipped out k equals 1, k equals 2, and I started with k equals 3 here. So I'm going to go minus k equals 1 to 2, k plus 1, k plus 2. Well, 1 to 2, that's just two terms. So I can actually just do that. So I'm going to go 1 plus 1, 1 plus 2 plus 2 plus 1, 2 plus 2. And this is equal to 18 right in here. Okay. All right. So now keep that in mind because we're going to subtract that constant later once we've combined these things here. Okay. So now also what I want to do is I want to k equals 3 to 50. I'm going to go 2k squared minus 2k. So I brought the 2 into both of those there because what I'm going to do now is I'm going to combine these two summations because they now have, right, so look, k equals 3 to 50, k equals 3 to 50. I can combine them into one summation. So how I'm going to do that, I'm going to write k equals 3 to 50 of 2k squared minus 2k minus k squared. You need to distribute that negative to both of these, all these things, minus 2. Right, don't forget this negative goes to here, goes to here, goes to here. Okay. And then minus 18. That minus 18 is outside of my summation. So be careful, because you don't want to subtract 18 from everyone. That's going to be wrong. It's just going to be a constant term. So this is going to look like k equals 3 to 50. I'm going to combine like terms. 2k squared minus 1k squared, k squared, minus 2k minus 3k minus 5k. And then I'm going to get minus 2, minus 18. Okay. So I do the whole summation, right? 3, for all intents and purposes, if I'm only doing a couple, you can actually do it out and get a number. For more than just a couple, more than a handful, you leave it as a summation formula. How you would evaluate this, you'd write a program to loop through and actually give you a number, and then you'd subtract 18 from that at the end. Okay. Alrighty. So the rest of the chapter section is definition after definition after definition. So I'm just going to number them. So we've got a whole bunch of definitions. But these definitions are going to help you work through the problem. They're going to give you shortcuts for handling summations and things that you need to do. So our first one is called Finite Differences. Okay, so we've got m and n are integers, where m is less than n. F is our function, and the domain includes m to n, right? My delta function, this is the subtraction. Delta means I'm going to subtract these terms. Our domain also has m plus 1 to n. Okay. So my delta f of k equals f of k minus f of k minus 1. Definition number 1. Definition number 2, linearity is the same for our delta. So linearity of differences. A and B are constants. F and G are functions whose domains include m to n, interval of integers. So my delta of A, f of k plus or minus b, g of k is equal to A delta f of k plus or minus b delta g of k. Deltas are difference function, right? So we had summation, which was an addition, and delta is our difference. Okay, but what's actually happening is we're taking a difference of things. Sometimes you're taking a difference of things within a summation. So you're going to be combining stuff. Okay, definition 1, definition 2. Definition 3. There's what's called a telescoping sum. We cover this actually quite a bit in calculus 2. We do there's a certain type of series called a telescoping series. M to n are integers where m is less than n. F is our real function whose domain includes m to n. We've got a summation, k equals m plus 1 to n. Delta f sub k equals f of n minus f of m. What this means is I'm summing up a difference. So I'm saying on the first summation I go f1 minus f2 plus f2 minus f3 plus f3 minus f4. It's telescoping because when you look at it all in one, some of those f's are going to cancel out, and I'm basically left with the end minus the beginning, essentially. Okay, so this is where we're at. That's what we call it a telescoping, because it goes from a really long thing. It's like those old telescopes where it collapses down into one. Okay, so we've got a subset of definitions here for how I handle difference functions. So delta k equals 1, delta k squared equals 2k minus 1, delta k cubed equals 3k squared minus 3k plus 1. These are shortcuts, so you don't have to work your way all the way through. Delta b to the k plus 1 exponential b to the k times b minus 1. Right, so these are all shortcuts for you for evaluating when you have difference functions. Okay, b is a constant, so another one, I can do k equals delta k times k plus 1 all over 2. 3 k squared equals delta. I think you have to use some of these in your homework for this chapter. You won't be expected to memorize this stuff here, but it'll help you in knowing that there are shortcuts for working through solutions. That was a 2, sorry. 3, if b does not equal to 1, b to the k equals delta b to the k plus 1. If n is greater than or equal to 1, summation k equals 1 to the n of k equals n times n plus 1 over 2. This is a good shortcut. It saves you from having to add them all up. If I go, I'm going to sum up all the numbers from 1 to 1,000,000. Right, I'm just going to go 1,000,000 times 1,000,001 divided by 2. That gives me my, summation of all those numbers. Okay. My next one, we only have 2 more. If n is greater than or equal to 1, I told you this chapter has a lot of definitions. K equals 1 to n of k squared. These are shortcuts again. N times n plus 1 times 2n plus 1 divided by 6. This is going to save you time, right? So you don't have to add up all the squares. You just get this. 7. Exponential functions b to the n plus 1 minus 1 all over b minus 1. We're going to define when 0 to the 0 is equal to 1. We're defining that. Okay, and then that's it for the chapter. This is a lot of just information on the chapter. I'll scan in the lecture notes, lecture examples, and then post that later. And I'll post also the videos for the class later as well. Okay, guys. Don't forget quiz tomorrow on chapter 4.1, 4.2. Bye, guys. Have a great day.
Thank you.
Thank you.
Bye. Take care.